Good morning, everybody. We'll get started in just about a minute. Thanks for your patience. All right, let's go ahead and get started. Thanks to each of you for joining in this morning. As a reminder, this session is being recorded, and I will be sharing that recording in the announcements once I have the recording available from captioning. Let me go ahead and share my screen. Would somebody kindly unmute and let me know if you're seeing the course homepage right now?
Yes, ma'am.
Thank you very much. Just as a reminder, I did make the video available from last week. I was looking at the date going, wait a minute, just the 15th, but right, we didn't meet last Thursday on the 17th. So that's why there's no recording from the 17th. So the 15th was the last actual class lecture session that we had. So, if you're looking for the videos, remember that's where you find them as far as the recordings for our class meetings go. All right, so you can see here this week that we're dealing with 2D motion. So as I have been reminding you periodically that this whole idea of motion is one of the key aspects of this course. And so last week, you spent time getting comfortable with the idea of vectors because that's one of the primary tools that we use to help us establish, direction when we're dealing with a moving object. And then prior to that, we looked at 1D motion where we focused on some of the basic principles that we'll need to describe quantitatively our moving objects. So we're taking a step forward, adding to the types of motion that we can describe this week by moving from 1D motion to 2D motion. Okay. And so as a way of focusing our understanding of 2D motion, we're going to focus on two particular types of 2D motion. Just like when we dealt with 1D motion, we focused in on free fall as an example of 1D motion. We're going to focus on projectiles and objects moving in a circular type motion as our examples of 2D motion. Okay, so we're going to have to, grow and build on what we've already learned to help us describe projectiles and objects moving in a circular fashion, particularly orbit type motion. And then, we've up to this point, we hadn't really focused on air resistance very much. So we're going to have to go back now and kind of hone in on this idea of, how does air resistance play a part in this? Not that we're trying to quantitatively do anything, mathematically where friction is concerned, because that would be way too much of a task at this level for us. But, just talk about in general, how would the motion of an object, particularly a projectile, change if air resistance were part of the picture? And then we'll look at, of course, I always like to bring in some examples, and we'll look at, some examples of how we solve problems dealing with the projectile and for objects that are moving in a circular fashion. Okay, So that's where we're going. That's what these objectives here, you know, convey, the kinds of things we'll be focusing on this week. All right. What activities do you have on your plate? Well, of course, you know, since we're dealing with 2D motion, that's what your discussion is going to focus on. And that's due by this Saturday. I mean, that's a fairly consistent thing, unless, you know, we have a major reason why we, you know, we always focus on Saturday as our deadline date, right? And then you have problem set number 4 that's due by Saturday. Now, just as a reminder, you know, to make sure we're all clear on that, problem set 4 deals with vectors from last week, right? Because the problem sets always lag a week behind, okay? So, you know, with the discussions, you have an opportunity to deal with the current topic and kind of hash some things out with your classmates through the discussion. But your actual problem set, now that you've had a chance to digest some things regarding vectors, the problem set allows you an opportunity to dig a little deeper where that topic is concerned, okay? So are there any questions on where we're going this week or what you have due? Okay, all right. So you can see here that I have made some resources available to you on these topics. I pulled directly chapters 4 and 6 from the textbook and made them available here. So you don't have to go digging for them. You know, you have it right available. There are some videos that deal with 2D motion and orbit motion. Let's see. Yeah. A set of videos on both of those topics. And then, of course, you know, these supplemental notes, those are my notes, right? So I'm going to go into those and focus on those for you. And I'm going to try to get through as much as I can on both of those today. Whatever I don't finish today, we will finish the notes on Thursday. And then I'm going to focus on some examples. In particular, I have a nice example on circular motion that I want to share with you, you know, so that you will have some sense of what kinds of things you need to be able to do problem solving wise with these two types of motion. All right. Any questions on that? All right. So let's jump right in. So, you know, here's my my reminder. You know, this I can't stress enough the importance of spending some time with this stuff and having an organized methodology to how you study and prepare for this material. Okay. Because as you can see, it's getting a little bit, you know, we're adding a level of detail each time around, right? So in this packet, we're going to focus on projectiles. All right. So, so when we're talking about projectiles, we're using that as our example of 2D motion, but you know, we need to understand now that because we're dealing with 2-dimensional motion, we're actually dealing with motion where an object is confined to a flat surface. You can think of it that way. Now, in math, they use the term a plane, right? A plane is like a flat surface. So our object can move anywhere within that flat surface. So it can move in 2 dimensions, okay? And so they give an example at the motion, yeah, like the flight of a cannonball through the air. I like to visualize the idea of, you know, a baseball being hit like a pop fly in outer, you know, like to center field or something like that, right? That kind of motion is an example of 2D motion. And it says here, you know, hockey players skating on an ice rink. Well, the ice rink is flat. So if they're moving on the ice rink, then their motion is confined to 2 dimensions, right? And so, you know, because we're dealing in 2 dimensions, we're extending our our knowledge in terms of what we learned for 1D kinematics, right? We're only focusing on this from a kinematics perspective. And you remember, kinematics means what? Pure motion, right? We aren't concerned with forces at this point, okay? And so, in 1D kinematics, the object was confined to moving in a straight line, either a straight horizontal line, like the car on the track for problem set number 3, or free fall, where the object is moving, up or down, right? But now what we have to do is we have to extend that and say our object can be moving horizontally or vertically, right? And so we need 2 parameters to specify the motion, and we just borrow from the math folk, and the horizontal is X and the vertical is Y. Okay, you have to focus in your mind and think, now this object is not just moving horizontally, or it's not just moving vertically, it's doing both. And so we need to utilize an XY pair. Those of you who have done, maybe done some algebra, or, even some simple type graphing, you understand the idea of an XY pair. We're borrowing the Cartesian coordinate system as a way, right? Because with 1D motion, we use the number line, right? The number line, you have an origin, you have positive X, negative X, or if you're doing vertical, you have an origin and positive Y, negative Y. But now we're going to be doing both. So we need the Cartesian coordinate system and this XY pair as our reference frame, okay? And so while we are dealing with an object that is moving in 2 dimensions, we're gonna simplify that drastically, okay? And the way we do that is to simply say that even though the object is moving horizontally and vertically, we can separate those 2 motions, and they act independent of each other. So even though that baseball is moving horizontally outward and vertically up and down, we can snatch out the horizontal part of the motion and look at that independently. And we can snatch out the vertical part of the motion and look at that independently, right? So that simplifies our life tremendously, where these objects that are moving in two dimensions are concerned. So that's what they're showing you in the picture here, right? So they're taking out. Now, what you have to visualize in your mind is that horizontal and vertical motion are happening at the same time, but we're just looking at each of those independently. And that's why all the pink balls represent the vertical motion by itself, and all of the blue represent the horizontal motion by itself, okay? And so, let me backtrack on that. I'm saying that incorrectly. Let me be specifically clear. The red signifies an object that was just being dropped, so only vertical. The blue signifies an object that has horizontal, which are the black arrows, and vertical, the green arrows. Now, what you see is that even though those are 2 different objects, you see that the vertical portion of the motion for each of those, the red and the blue, is actually identical, right? If you look at the green arrows pointing down on each object, you can see at any instant, those arrows are exactly the same, meaning, remember, we use vectors. I mean, we use arrows to represent vectors, right? So the actual vertical motion of each of those objects is identical. Also, one of the things you notice is that, well, of course, the red object, because it's being dropped, doesn't have any horizontal. That's why you don't see any black arrows on the red. But for the blue, you notice that there are black arrows representing the horizontal motion. And notice that the size of those black arrows representing the vector for the horizontal motion are identical. Okay. And so the vertical motion of each of those objects, even though the blue has a horizontal component, is identical. Okay. And that the horizontal motion or the horizontal velocity of the blue never changes. So that simplifies our life tremendously, right? Because what? Because we know how to handle the vertical part of the motion for each one, which is identical. That's free fall. Go back and think to your pyramids. You have a pyramid that strictly focuses on free fall, where you have gravity, velocity, and time. And you can use that pyramid on the red because it's free falling, or the blue because the vertical part of its motion is free fall as well. Meaning only gravity is controlling the red object because it's being dropped, and only gravity is controlling the blue because as far as its vertical motion goes, it is also being dropped, if you want to think of it that way. Okay? It's free falling. Okay, as far as this illustration shows that. Now the question then becomes, well, if this object, this blue object, has horizontal motion, how do we describe that mathematically? Well, think about it. Its velocity isn't changing. So it's not accelerating horizontally. Vertically, it is accelerating because of gravity. Okay, so we know how to deal with the free fall, and we know how to deal with horizontal motion if the acceleration is 0. It just means this, you know, it's on horizontally, it's on cruise control, but vertically it's free falling. And it's doing both of these things at the same time for the blue object. Okay, so that means that then we have a clear-cut way to explain quantitatively the motion of this projectile, an object moving like the blue object that we just looked at. The red object is technically a projectile, but we're never going to call the red object a projectile. We're just going to say that's an object that's in free fall. We're going to call the blue object a projectile because it has horizontal and vertical motion. Okay, that's how we're going to distinguish a projectile from an object that's strictly free falling. Okay, and so you see here our definition of a projectile. This object is in motion. It is subject to gravity only as far as acceleration goes, and there's no air resistance. Okay, so that air resistance is 0. Okay, and that is what allows the horizontal velocity to remain constant. Right? How do we express that? Remember, x is what we use for horizontal. So Vx is constant, meaning horizontally, the projectile is on cruise control, meaning its velocity is not going to change. Remember, gravity does not affect horizontal motion. So since there's no air resistance, there's nothing to make that horizontal velocity change. All right. What about the vertical motion? Well, What they did here was to give you the equations of motion for a projectile's vertical component where only gravity is involved. Okay, you'll recognize these because we saw, if you think about, 2 weeks ago, 5 equations of motion for an object, and I simplified them for you even further by giving you a pyramid that deals with free fall. Okay, so in order to analyze a projectile's motion, and I might have to stop the share. Just tell me just for a moment. I'm gonna go to a whiteboard, and I'll make this whiteboard available to you. Okay, somebody tell me, can you see that whiteboard? Anybody?
Yes.
Oh, thank you so much. I appreciate it. Okay, so let's talk about the horizontal motion for our projectile. And I apologize for the quality of my penmanship, but this is because, I have to use the mouse to draw on this, okay? So let's talk about the horizontal component of the projectile's motion. Remember, we're dealing with a projectile here. Okay, so the first thing we know is that the horizontal acceleration is equal to 0. And I always like to put units on it to kind of, remind myself of the property I'm dealing with, okay? So if our projectile can't accelerate horizontal, that means, because we use what? We use X for horizontal, okay? So here, that means that Vx is constant. Okay. And we can go back and think about our, our pyramid in terms of this horizontal motion. If we just think about this right here. Okay. So remember, A goes right here, but A is equal to 0. Okay. And then you have, remember, you have T here, and you have V, F minus VI. Well, if this is 0, that means you don't even have to bother with that. The only thing you have now is what? VF minus VI. Here, think about it. Over T equals 0. Right? So that means here that VF has to equal to VI. Okay. So if the acceleration for the horizontal motion is 0, and we know for a projectile that is 0 because gravity doesn't work horizontally and there's no air resistance. So the projectile can't speed up or slow down. Okay. All right. We could also, well, I was trying to close my pyramid there. All right. We could also look at the vertical. All right. So for the vertical motion, for vertical, we're using what? Y. Okay. And so, you know, we know that this is in free fall. And so that tells us automatically what we need to be focusing on for free fall is what? Here's our pyramid, right? So we got G, T, and then VF minus VI. Please do not mix these two up because this VF and VI is for X. This VF and VI is for Y. They're different. And remember that what? A equals G equals 9.8 meters per second squared. And I'll just remind you that that's what? Down. Okay. All right. So you see now, to analyze projectile motion, we really don't need to do much of anything else. There's only one other equation that you need to know for the projectile, and that is the range. Because we want to know how far out our projectile is going to go. Okay. So, you know, here's like our starting point. Everything is 0 here. Okay. And then we want to know our X final here. Okay. So our X final. Okay. And that equals to our, you can write it either way you want. Okay. You can write it X final equals VI times T. Okay. Or you can write it as VF times T. Why? Because VF and VI are always equal, right? So it doesn't matter which one of those you choose. Okay. Now, what you have to keep in your mind is that this T right here is the same T right here because what? The time is the same for both of the motions, right? Because you can see here that this projectile moves, you know, it moves vertically, right? Well, let me undo that. Okay. We have, I like to think about it as, okay, if you're starting from 0 here, then our projectile goes up to a certain height and then comes back down to the same starting height in this particular situation. So yeah, I can just label that Y. Okay. That's just to give you a sense of that up is positive, and if it were going below that, it would be negative. Okay. All right. So this up, you know, up and down kind of motion is being controlled vertically by free fall, and the outward motion is stuck on cruise control. All right. Does that make sense to everybody?
Yes, ma'am.
Okay. So, you know, when it comes time to problem solve, we're dealing with projectiles, you can just go back and do what you've been doing, right? The vertical is free fall. You know how to deal with that. The horizontal motion in this case is even simpler because the velocity can't change. So the only thing we figure out is how far out it went. And that's dependent upon how much time it spends in the air. Okay. All right. So I'll make sure you have access to this whiteboard. I'll copy it and put it in the notes, like when I post the recording. Okay. So see, I made things simpler for you. You don't have to worry about these equations here in the boxes. We just stick to our simple way of dealing with the projectile. And it's on me to make sure that, you know, questions are framed in a way that you can go to these tools as a means of dealing with your projectile motion. Okay. We're not going to worry about the maximum height of the projectile. And they do give a range formula, but I don't expect you to use that range formula because of the fact that it uses trig. This sign of stuff is a trig thing. And we're just going to stick to this to find the range of our projectile. Okay. All right. So that's pretty much the projectile stuff that I wanted to get into with you. And I'll make sure you have access to that whiteboard so you know where you're going in terms of the in terms of the problem solving, what resource you utilize. All right. Any questions about that? All right.
No, ma'am.
Thank you. So now let's get into the circular motion notes, because remember, my goal is to give you enough background today so that on Thursday we can do some sample problems. Okay, that's the goal here. So our primary goal here with circular motion is to get some background so that we can deal with orbit motion. That happens to be one of my favorite things to think about, and that's primarily because we actually have some great examples to look at where orbit motion is concerned, not just the planets, but all the satellites that are out there. I apologize, folks. I'm looking at my phone because we're having a major plumbing issue at my house right now. So trying to get somebody out there to repair it. And I'm just kind of trying to follow up to make sure that I got some help on that one. So I do apologize. Normally I wouldn't pay attention to it, but well, when your house is flooding, when you flush the toilet, what are you going to do, right? Okay, so rotational motion. So now we're not looking at an object that's moving in a straight line. Okay. We're looking at an object that's moving in a circle, but we're gonna take the simplest type of circular motion. Okay. And they mentioned something about Newton's first law there. Ignore that. That's not relevant for us. Okay. We're going to approach this rotational motion from a simple perspective, and we're going to look at it from a kinematics perspective. We don't care about force at this point. So Newton's laws is not even something that's relevant is there, but it's not what we're going to focus on. Okay. So we're going to focus on uniform circular motion. And that is for an object that's moving in a circular path, but with a constant speed. Okay. A constant speed. Now, here's what you have to wrap your head around for this object that's moving at a constant speed. Even though it's moving at a constant speed, the velocity is still changing. And that is because the direction is changing. We can get a quick visual here. Let me just open this up. And I'm gonna go to one of my nice simulators here, because I like the way that they, for this visual that we need here to really help us make sense of this. Let's go to, and those of you who have me for lab today will appreciate this simulator because it's one that you will be using. So I just hit the play button and let it load up. So we're gonna go in. Okay. And I'm using this as a simple visual. We'll talk about the aspects of this motion that are relevant for lab when we get to lab. But for now, we just want to focus on it as a visual to help us understand what's going on in a circular motion for this object. Okay. So you can see here, I have an example of the Earth going around the sun. okay? And we're simplifying the orbit and saying that the Earth is going around the sun in a circular orbit. Now, actually, that's not quite true. The orbit is elliptical, but you know, my favorite saying is also good enough for government work. Okay. All right. So you can see the velocity is being represented by the green arrow in this case. And notice that the length or the size of our velocity vector doesn't change. The length of the arrow represents the size, right? How much, right? But notice what is changing is the direction that the green arrow points in at each time, at each instant, right? If we could just pause it, see in this particular situation, notice the direction that the arrow is pointing. If I let it go a little further, notice that the direction is pointing in is different, right? So we have to go back and remember that velocity has two components. The speed part in this case, which is the size of the green arrow, which is fixed, and the direction, whichever way the green arrow is pointing. So since that direction is changing, our velocity is changing. Now, who knows the term that we use when we say an object's velocity is changing? What is it doing if its velocity is changing? Nobody knows the term for when an object is in motion and its velocity is changing? What do we call that? I don't know if that means you don't know or you're not wanting to share out. Either way, I don't know. I have to take that from my perspective as problematic, because that should be something that rolls off your tongue at this point in the course. If an object's velocity is changing, it means it is accelerating. And in this particular case, we have acceleration being produced, the blue arrow, just because the direction of the object's velocity is changing. So this object is accelerating without having to hit the brakes or hit the gas. It is accelerating because if you think about it in terms of a car, we're turning the steering wheel. So we're changing the direction that the velocity points in, producing an acceleration, the blue arrow. Now I know on here they call it gravity force, gravity acceleration for us, right? Now the other thing that you notice about this acceleration that's being produced simply because the velocity is changing, the direction of the velocity is changing, I should say. This blue arrow representing the acceleration always points toward the center of the circle. Notice that. It always points toward the center of the circle. And I'm talking about the blue acceleration arrow that's attached to the Earth, because it's the, it's the acceleration of the Earth in this case that we care about. Okay. So this is an example of orbit motion. And in this case, the Earth is accelerating toward the center of the sun strictly because as it moves in a circle, its direction, the velocity, the direction of its velocity changes. And we call that uniform circular motion. Circular motion where the speed is fixed or uniform, okay? So those of you in lab will have an opportunity to use this simulator to get some more interaction with this whole idea of orbit motion. But what we want to be able to do in this situation is to quantify this centripetal acceleration. Centripetal is a word that means center seeking. It's German, it means center seeking. And because this object is experiencing an acceleration that always points toward the center of the circle, we call that centripetal acceleration. So the things that we want to know, because our job is to quantitatively describe this moving object. Quantitatively means we can measure some properties and then we can express those measurements in the form of a formula, right? Okay. Formula which helps us to understand the relationship between the various properties that we measure. Well, one of the properties that we're measuring in this case is what they call, you'll hear it referred to as different ways, the tangential speed, the instantaneous speed, okay? The idea that it's speed. So if you go back to your definition of speed, that's distance divided by time. So the distance as our object moves in a circle is the circumference of that circle. That's the distance it covers if it makes one trip around, the circumference. Well, go back to your formulas for circumference, 2 pi r. And then the time that it takes. If you look at this, imagine we started our clock right here. And now when it comes back to right here, the question is, how much time did it take? Well, we know for the Earth, that's what, a year, right? To get back to the original starting point as it moves around the sun. But in general, for any object, we call that time the period. So the time that it takes to go around once is called the period, okay? So for our object that's moving in a circle, we can find the speed by taking the circumference, 2 pi r, divided by the period, capital T. That's the time it takes to go around once. And once we're able to find the speed, then we can utilize that to help us find the amount of acceleration. Remember, this acceleration is pointing toward the center of the circle. We call it centripetal acceleration. That's why there's a subscript C on it. A C stands for centripetal, or you can think it as center seeking, right? How much acceleration toward the center of the circle. And so what we do is we take that speed, we square it, and we divide by the orbit radius, in this case, the radius of our circle. And we know you measure the radius from the center out to the edge of the circle, right? Okay. So those are the two things that we want to know, the speed and the acceleration. Okay. And we know the direction for this is always changing. So we just focus on the size. And we know that this always points toward the center, the centripetal acceleration. So we just focus on the size. How much? How fast is it moving? And how much is it being accelerated toward the center of the circle? Those are the properties that we focus on. Now they talk about force down here. We'll come back to that. Okay. And so that's what they're explaining in these drawings, that the centripetal acceleration always points toward the center. I don't care for their visual, because I think it's much easier to see that the acceleration is always pointing toward the center here, okay? And we're not gonna focus on force. So there we go, all right? So we have our background that we need to tackle example problems that deal with projectiles and example problems that deal with orbit or circular motion. And we're gonna take a look at some sample problems on Thursday. What I need to know from you right now is, what are your questions at this point? Whether it deals with projectiles or circular motion, what are your questions at this point? Okay, so that'll be a wrap for today. Thursday, we'll get together. We'll look at some sample problems. Please, if you have questions between now and then, don't hesitate to reach out to me. And for sure, you know, on Thursday, as we work through problems, if you have questions, I definitely need you to be asking, right? So I want to thank everybody for joining in this morning. I'll get the recording out there hopefully in a day or so. And everybody have a good rest of your day.